Good evening, ladies and gentlemen. I hope that you all had a good day and that your second day on campus wasn't too bad. And yes, today has a unique date. It's the year 2022, the second month, and it is the 22nd. So now, just to make it complete, we have to wait till tonight, 10 o'clock. That will also be 2022, and with the minutes and seconds also to be 2022. So this was also a unique date and time we can see today. So while we are waiting for more of our class friends to join, you've probably all seen the link I posted for the Discord channel and the WhatsApp group. So you all are more than welcome to use both of them for communication. One other thing is, if you have any formal requests, please send me an email with a formal request, such as you have a problem with work or something needs to be changed, because if I need to change something at a department or the faculty, it needs to be a paper trail, and it helps to have a email thread from the beginning. Also, just make sure if you send an email, I'm a bit pedantic on it because I receive lots of emails per day. So on a good day, I will receive a minimum of about 70 emails. So if you send an email, just take notes. I will get to your email and I will reply to it most likely within a day. But if it is very important, just in your subject lines, say something urgent, NB, important, and something like that. And please, for your email communications, it's not a text message, it's not a WhatsApp group, so please use formal structure for your emails. I'm going to be a bit pedantic about that, and then everything should be fine. So for tonight's class, before we begin, I thought of showing you guys two different videos. The first one is of a conference I attended last year, just a short video from that conference about black holes and Event Horizon Telescope, just something to prickle your interest further in astronomy. Then the second video is going to be a short overview of the first chapter that we're going to do. So let's start with the first video I want to show you guys.
Who organized this meeting and brought us all together. I really appreciate her work. So we're extremely fortunate to have Sarah Ision to talk about. She's an expert on black holes, and in particular on the black hole at the center of our galaxy, Sagittarius star. And she and her collaborators used Cassper instrumentation to make the very first images of black holes. And I think she's going to tell us all about that. Thank you, Sarah.
Thank you very much. So it seems screen sharing is not possible. Could that be enabled?
Hey, Sarah, try again.
Okay, there we go. Thank you. All right, thank you very much for inviting me to talk about our project. It's really exciting. I'll try to spend a lot of time on the instrument and then give some context on science. Of course, I'm a member of the EHT, so everything I say is on behalf of our amazing collaboration, which is very diverse, and we have, telescope staff and engineers and scientists working on lots of different aspects of the project. So first off, why do we care about imaging a black hole? Why is this important? So first of all, black holes are mathematical occurrences of the theory of general relativity, and they also exist as astrophysical objects, which is quite amazing. They are very extreme environments where time and space come to a halt, and physics is at its most extreme. On top of that, we believe that supermassive black holes reside in the centers of most large galaxies, and they eject these streams of matter, which we call jets. These jets pierce entire galaxies into galaxy neighborhoods, sometimes thousands of light years in length, and they're the most energetic and powerful process in our universe, but we don't really know why that happens. We think the central engine is the supermassive black hole. We think magnetic fields and pressure and gas forces play a role, but we don't really understand what is the mechanism that causes these. So in order to understand where this comes from, we need to look at the central engine, which is a supermassive black hole. We have two supermassive black holes big enough to image from Earth, the one at the center of our galaxy, Sagittarius A star, and the one in the galaxy M87. M87 you can see in the corner here. It is over here. It has a well-known jet. It is actually the first astrophysical jet ever observed by humanity. It was observed in 1918 with the Lowell Observatory in optical, and they saw this stream of matter coming from this tiny point, which is the galaxy itself. And in fact, what powers it is the supermassive black hole. So if we look up the night sky in the Virgo constellation, there is a galaxy called Virgo A, or M87, 55 million light years away from us. Because there is a lot of gas and dust between us and the center of the galaxy, we need to observe in radio waves. Although this stream of matter, this stream of plasma is visible in the optical and radio, only radio can peer all the way down to the center because it's not absorbed by gas and dust. So if we use radio waves at higher and higher frequency with larger and larger instruments to increase our resolution, we can zoom down, follow this stream of matter all the way down to its core, which is where we observe with the EHT, the black hole M87. And with the EHT, we observe at a frequency of 230 gigahertz, which is the frequency high enough so that we can peer through all the way down to the black hole. And also, it just happens to be the frequency that gives us a resolution that lets us image the shadow. Now, in order to piece together a synthesized Earth-sized instrument, we use a technique called very long baseline interferometry. So I'll explain a little bit how this works. So say we have a source very far away, so that if we are in the far field regime of radiation, because it's far away, the waves that arrive on Earth are plane waves. Because of the Earth's geometry or curvature, there is a time delay between the arrival of a specific wave at each telescope. Now, the distances between telescopes tell us information about the image. Telescopes close together tell us about information on large scales because they see a lot of signal in common. And telescopes further apart see smaller signal in common, so they see a small scale structure in the image. So by combining many different telescopes at different locations on Earth and at different distances from each other, we can piece together different directions, orientations, and scales in our image and combine them. So this time difference is, however, quite important because we want to be able to correlate the signal received at each telescope. So in order to see what signal is in common, we need to time tag our data. And we do this using atomic clocks called masers. They're hydrogen maser transitions that time tag our data with very precise time. And these clocks are so precise, they lose about a second every 100 million years. Now, once our data packets are time tagged, they're recorded onto hard disks. We essentially freeze the light received at each telescope and record them and then combine them at a later time where we can then align the signals and reconstruct an image. So the EHT project is a 10-year project. The first multi-baseline, multi-telescope observation was done in 2007. Then as we expanded the array, we've added more and more telescopes, and some telescopes got decommissioned, so we lost some as well. And then finally, in 2017, we made our famous observations. In 2017, we had 8 telescopes at 6 different locations, 6 single dishes, and 2 phased arrays. Now you'll notice all of these telescopes look very different from each other. This is because we did not build them. They were built for completely different science, so self-standing science. And we just happen to borrow them because they can observe at 230 gigahertz, the frequency at which we need to get to M87. And they are at high enough and dry enough places and at the right places where we can reconstruct an image from different scales. So high and dry places, some of the most dry deserts on the planet, is extremely crucial for our observations. Because we're observing at such a high frequency, we are very susceptible to water vapor and turbulence in the atmosphere between us and space. And the Earth's atmosphere scrambles our signal and absorbs it because of the water vapor. So we really need to pick the right sites that maximize our signal. And our signal is very weak. So our black hole image has a total flux density of about 0.6 Jansky, so almost half a Jansky. And if you take into account all of the radio observations made in the history of humanity, it is less energy contained in that than a single snowflake dropping to the ground. So we're looking at really, really small signal, and it is really crucial that we build sensitivity. So building sensitivity with the EHT means increasing a recording bandwidth and frequency bandwidth. So across many years of our radio observations, we had different systems. The ones that matter the most is our current system here with the Roach 2 digital backend and the Mark 6 recorders. So our 2017 observations recorded at 32 gigabits per second. So this is following, the law of the doubling bandwidth, which is quite amazing that we're able to see this biennial doubling with our own observations and equipment. So we observed at 32 gigabits per second with 2 polarizations and 2 gigahertz basebands. So 2 polarizations because we want to make polarization maps of the magnetic fields around the black hole, and I'll show a little bit of that later. Since then, we are now at 64 gigabits per second, so we've doubled our frequency bandwidth as well to make more polarization and frequency studies. So the signal we receive at the telescopes is, of course, an analog signal, and it's 230 gigahertz, so it's very high frequency. We down convert it to a 2 gigahertz baseband with block down converters, and then we digitize it with our Roach 2 digital backends with 2-bit sampling. And then they're recorded onto our Mark 6 recorders. This is one.
Sorry guys for pausing. Before we continue, can anybody hear the audio fine on this video? Okay, cool. I will also give a link to this video afterwards as well.
One example of one Mark 6 unit. There's 4 boxes here, which we call modules. These Mark 6s, one records at 16 gigabits per second. We need 4 Mark 6 recorders to record at 32 gigabits per second with 2 polarizations. So there's 4 modules per Mark 6, and each Mark 6 contains about, each module contains 8 helium-filled hard drives, which you can see stacked here. All our Mark 6 recorders are equipped with custom cooling for high altitude use. All our equipment needs to be heavily tested at high altitude in these kind of pressure chambers, because at sites we're at least 10,000 feet above ground, sometimes 15, 16,000 feet. So we definitely do not want equipment to overheat. Also, including our equipment is not well exercised. We only observe about 2 to 3 times a year, including our dress rehearsals where we practice observing. So we really need to make sure all our equipment can easily start up and not run into too many issues when we do observe. So this is what one full backend looks like. This is from Spain. And you can see here are 4 Mark 6 recorders. We have our digital backends here, our digitizers, our down converters. And for the total of our 2017 campaign, we used 92 individual modules for 736 hard drives. In total, we recorded about 3.5 petabytes of data across our 5 triggered days. So we observe for a 12-day window during our EHT campaign, 5 days to trigger for observations, and we need to keep a very close eye on the weather. As I mentioned, we have stations at very high and dry places, but that doesn't guarantee best weather all the time. Especially in April, where when we observe, it's kind of marginal weather everywhere. So we need to look for these pockets of good weather for half the Earth, which is really difficult, a really difficult task to coordinate. And we were really lucky because in 2017, we had probably the best weather we've ever had, and I don't think we'll ever have this kind of weather again. So we keep a very close eye on current and forecasted weather and telescope operations to figure out when to trigger. So here are some nice pictures from our 2017 observations. On top of having operational local staff at the telescopes, we also send our own EHT members to the telescope. Here are some pictures of our EHT members with local staff. And they act as our local experts for backend equipment and for the telescopes. Then once we record the data, they get shipped to our correlation facilities, these two places, MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy. Each facility correlates about half the data. So at correlation, we combine the signals from each telescope, we align them, we throw away all the noise that is telescope specific, only to keep the signal seen in common between pairs of telescopes. And it takes into account the Earth's curvature and these timing effects that we measure from our equipment. One thing that it doesn't take into account is, again, the atmosphere. And atmospheric effects, because we have this jitter in our phases in the data, it prevents long averaging. So if we average turbulent data, we end up destroying our signal instead of piling up and building signal to noise. So we need further data calibration. The advantage, though, is that we record at very high bandwidth. And so we do have the signal to noise to actually track atmospheric changes in the data. From that, we can refine corrections from correlation and remove the effects of the atmosphere. So here's an example. So this is real data from EHT. So in yellow, you can see amplitudes, and in blue, phases from 3 baselines or 3 pairs of telescopes. Now, because we expect the phases from the source to vary very slowly, these few second phases, so this is over time over 400 seconds, these few second phases changes are entirely due to the local atmosphere. And so if we look at these 3 baselines, these are 3 pairs of total of 3 stations. We can actually triangulate which changes actually happen at each station. And because ALMA is the most powerful radio astronomy observatory in the world, and it brings amazing sensitivity, the baselines to ALMA allow us to have amazing signal to noise to actually track atmospheric phases on second scales and actually remove them. So once we remove them, this is what the phases look like. So now if we average down over our entire scan over a few minutes, we build sensitivity. We don't destroy signal anymore. And this is all real data. This is really what it looks like. And it's really amazing because of our high recording bandwidth, we're able to build enough sensitivity to track and remove effects of the atmosphere and really build our data, build our signal to noise, and build confidence in our data. Now, of course, understanding the data is one step, but understanding telescopes is another. We need to understand how our telescopes work, what are their sensitivities, so that our detections, which are now at signal to noise, go into a flux density scale. So we need them in Jansky so that we can make an intensity map. So in order to do that, we need to take into account, again, the sensitivity from the atmosphere, the size of the dish, different surface elevation effects, signal chain, noise level, and also polarization leakage. Now, I mentioned that our total intensity image was about half a Jansky. The polarization signal is even less than that, way less than that. And so polarization leakage is very important to remove because it creates false signal in polarization, and we really need to remove it very accurately in order to make polarization maps. But there's a trick to it. So we decouple leakage and source signal using the Earth's rotation. So because we observe for such a long time, when observing track is about 8 to 9 hours, each telescope sees the source move in an arc on the sky. So the signal from the source, the real polarization signal, is expected to move over time, but the instrumental contribution from the telescope stays put on the ground. So if we combine each arc from the telescopes, we can separate those contributions. So our entire data path from the raw signals, which is 3.5 petabytes, all the way down to an image, which just can be sent on your phone, is about 12 orders of magnitude in data reduction. And the most powerful data reduction actually happens at the calibration stage. So now that we have our final data, we can start imaging. And we use, again, the Earth's rotation with the technique called aperture synthesis. So because our telescopes are at set location on Earth, as the Earth rotates, we're sampling different parts of our image. So the Earth's rotation helps us build our virtual mirror, which you can see here. So our coverage is in Fourier space. So we're sampling different frequencies in our image. So as M87 becomes visible, we get different pairs of telescopes that give us different tracks on our coverage. And as we pile these data in time and in space, we can see how our image improves. So you can see here how as we build up our data and our coverage, the image takes shape. So we imaged M87 with 3 different softwares. This one was a traditional technique for historical VLBI. These 2 were designed for EHT-specific issues dealing with, systematics from our high sensitivity and our sparse coverage that we have. And all 3 gave very good answers. We tested all of these softwares against synthetic data where we knew the ground truth to make sure that we picked the right optimal parameters for our software, and this is the final results. So these are the 3 software images for April 11 observation, and in fact, the famous image I'm sure you've seen of the black hole is simply the average of these 3. So that is the first image of a black hole. But during our 2017 campaign, we triggered 5 observing days. 4 of them had M87, so we have 4 individual observations of this ring. This one was April 11. And here are the other 3. So as you can see, over our 4 days, we don't see significant changes. Every single day gives us a ring of the same size, right on the bottom with a dark spot in the center where the black hole shadow is. In polarization, which we just released a couple of months ago, we get these beautiful images. So on top of our total intensity ring, we added the information from polarized light. You can see that polarized light only lights up the southwest part of the ring and gives us this kind of spiral structure in the polarization angles. So we get a spiral polarization structure across our 4 days, and it looks pretty similar across the days as well. I'll explain everything that we learned from this. First, we measured the size of our black hole, which was 42 microseconds on the sky, which is because we know the distance of the black hole, we were able to measure the mass, which is 6.5 billion solar masses. M87 is one of the largest and most massive black holes in our known universe. I really love this comic because it actually shows us the scale of this image. Although it's 42 microseconds, it's the size of seeing an orange on the surface of the moon with your naked eye. It is actually bigger than our solar system. So you can see the sun at the center, Pluto, the orbit of Pluto around, and Voyager 1, which is the furthest human-made object that we've sent out, just at the edge of the shadow. Now, the next step is to understand what exactly we're looking at. So we've imaged it. We know it's a ring. We know it has a shadow. What does it tell us about the physics? What are we learning? So in order to do that, we simulate a black hole and its environment. So we use fancy simulations that take into account the space-time around the black hole with general relativity and the physics around it. So we have matter orbiting, falling into a black hole, which we call the accretion disk. And it also spews out these jets of plasma. And then these disks and jets are also threaded with magnetic fields, which help push in and out material. And there's a black hole at the center. And then because of the very hot gas temperature, the gas is not atoms, it's ions and electrons. And so because we have electrons, magnetic fields, if we have very fast moving electrons spiraling around magnetic field lines, they emit synchrotron radiation that is polarized, and that is the emitted light that we observe with the EHT. So from different types of physics that we try to understand, we made a simulation library. So this is our total intensity simulation library to try to understand the signatures of our ring. There are lots of different ones here that have different, gas properties, magnetic field properties, but they all have something very clearly in common. They all have, a dark patch at the center and a bright ring around it. So why is that? Why do they all show the same thing? It's because this signature in our main image is a direct effect of gravitational lensing. Because we have such a strong pull from the gravity of the black hole, we have light rays from around the black hole that get bent by the gravity of the black hole. And as seen from a distant observer, if you have a lot of light rays, which is the case with the gas around the black hole, as a distant observer, you will see this kind of puffed up shadow surrounded by a ring of light, and that's exactly what we observe. Now you'll also notice that our ring of light is not smoothly uniform. It has a part that is brighter on the bottom. The reason of that is because of the inclination we're looking at. We're seeing a full ring. We're looking almost straight down the barrel of the black hole. And one side is brighter than the other because of Doppler boosting. So the side that is brighter is coming towards us, and the fainter side is going away from us. So another thing we learned from our simulations is also that the gas rotation around the black hole orbits clockwise, and that the spin of the black hole is pointing into the board, into the screen. Then we also looked at polarization simulations. So we have our polarization images. We want to understand what do the magnetic fields look like and whether they actually play a role in launching this famous jet that we see in M87. So we made polarization simulations, which you can see on the left with perfect resolution, and on the right what we would see with the EHT. And we compared these polarization maps. So what it teaches us is that if you have a black hole with an accretion disk with threaded magnetic fields, if you have weak magnetic fields, they would kind of look like concentric circles, the field lines. And then the synchrotron radiation that would come from these field lines would look like spokes on a wheel as seen from Earth. So we'd make polarization maps that would look like, that stick out like this, just like the animation. Now, if you have a very strong magnetic field, you will get the opposite effect. You will get spokes on a wheel, magnetic field lines, and then the synchrotron radiation would look like concentric circles as seen from Earth. So this is what our image would look like. But as you remember, our polarization image looks like a spiral, right? And so it means it's kind of in between weak and strong. So if we have a spiral structure of the magnetic field, the synchrotron radiation that we see from the black hole is also a spiral. And so we learned from this that the magnetic field strength around the black hole is about 4 to 30 Gauss. And it has a spiral structure that has a vertical component. The interesting thing about the vertical component is that it means it's able to push gas out, which means that it could be the cause and the direct link between the black hole, this magnetic field, and the jet launching. So that is where we stand now with EH2 results. So what's next for us? We've added new stations since then. We just observed in 2021 with the added Greenland telescope, Cape Peak telescope, and NOEMA array. We're hoping to add a telescope in Africa, but we're thinking about really long term as well, which is the next generation EHT. So with the next generation EHT, we'd like to have, because now we have the sensitivity from our large dishes, like ALMA and like NOEMA. So we'd like to put small dishes at lots and lots of different places on Earth to fill our coverage. So we're no longer sensitivity limited. And what's really cool is that say if we have a simulation here of a black hole and its jet, what we would see with 2017 is just the dominating ring that we see in our images, but we know this jet exists, and we don't yet have the sensitivity and coverage to be able to image it. But with the NGHT, we'd be able to make images and link directly the ring to the jet emission from the black hole. And this will really help us understand how the jet behaves and how it connects to the black hole. And we want to extend to space. We'd like to have longer baselines, so no longer limited by the size of the Earth. We'd like to have faster orbiting in low Earth orbit to fill our coverage and go to higher frequencies. Even if we have an entirely space-based array, we're no longer limited by the Earth's atmosphere, so we can go to like 1 terahertz and observe. But next generation EHT means next generation challenges. This is my final slide. Just to think about where we're going, because we're adding so many more telescopes, we need to look at our monitoring and control development. We can't just keep sending telescope experts to sites, especially if we want to observe more often. We're going to have a lot of data, so we want to expand from our 64 gigabits per second to 256 gigabits per second. We need to think about data storage and real-time correlation. For ground-based array antenna design, we need to look at smaller dishes, which should be sufficient given the current sensitivity. For a space-based array, we're looking at whether we have a single orbiter with our ground array, which allows for quick filling, or an entirely multiple orbiter system, which allows for very slow filling but very sharp images. Then we want to build sensitivity in space. If we want a wide bandwidth and large data rates, how do we get the data down? We can't just keep hard drives there, and we can't send an airplane to get it. So we need to think about how to downlink this kind of data. And also timing in space. So our Maser clocks that we have at the sites are the size of a mini fridge, and we can't really afford to put a mini fridge into space. So we need to think about compact solution for timing, which is really crucial for our signal for VLBI. So I'll stop here. Thank you very much, and I'll take questions.
Thanks, Sarah. That was great.
So what did you guys think about this video? So later on in this course, we're going to do a bit of an overview on black holes. We're also going to discuss telescopes itself. So this is just something interesting to show you what's happening in the astronomy world, what's happening in the astronomy community. So in the astronomy community, you can do anything from building telescopes, designing the instrumentation that needs to go on those telescopes, to do the computer science behind it, develop algorithms to do the imaging of the objects we observe. We also use, in astronomy field, we also need to solve big data problems. So you can see we start with observation with 3 petabytes that needs to be reduced. And then we get to the physics itself. What physics can we learn from the objects that we observe? So there's a lot of aspects from astronomy. So in the chat, I've just pasted the link to this video. So you'll see the video starts at more or less 30 minutes. But this is a long video of all the different talks for that day in the conference. So that is just something interesting I thought I'd show you guys. Now the next video I want to show you is where do we start with our first lecture in astronomy. So let me play the next video.
Oh, hey. So
Sorry, seemed something went wrong there. Let me try this again.
oh, hey, sorry. I don't mean to be rude. I'm just trying to figure out how far away my thumb is. How? Parallax. Centuries ago, people thought the stars were holes in a huge crystal sphere letting through heavenly light. It wasn't clear just how big the sphere was, but it was pretty dang big. I have some sympathy for them. By eye, and for all intents and purposes, the stars are infinitely far away. If you drive down a road, you'll see nearby trees flying past you, but distant mountains move more slowly. The moon is so far, it doesn't seem to move at all compared to nearby objects, and it's easy for your brain to think it's much closer, smaller, and actually following you, which is a bit creepy. Sometimes people even think it's a UFO tailing them. Finding the distance to something really far away is tough. It's not like you can just pace off the distance. Or can you? The ancient Greeks knew the Earth was round, and there are lots of ways to figure that out. For example, ships sailing over the horizon seem to disappear from the bottom up, as you'd expect as they slip around the Earth's curve. But how big is the Earth? Over 2,000 years ago, the Greek philosopher Eratosthenes figured it out. He knew that at the summer solstice, the sun shone directly down a well in the city of Syene at noon. He also knew that at the same time, it was not shining straight down in Alexandria and could measure that angle. There's a legend that he paid someone to pace off the distance between the two cities so he could find the distance between them. But more likely, he just used the numbers found by earlier surveying missions. Either way, knowing the distance and the angle, and applying a little geometry, he calculated the circumference of the Earth. His result, a little over 40,000 kilometers, is actually amazingly accurate. For the very first time, humans had determined a scale to the universe. That first step has since led to a much longer journey. Once you know how big the Earth is, other distances can be found. For example, when there's a lunar eclipse, the shadow of the Earth is cast on the moon. You can see the curve of the Earth's edge as the shadow moves across the moon. Knowing how big the Earth is and doing a little more geometry, you can figure out how far away the moon is. Also, the phases of the moon depend on the angles and distances between the Earth, moon, and sun. Using the size of the Earth as a stepping stone, Aristarchus of Samos was able to calculate the distances to the moon and the sun, as well as their sizes. That was 2,200 years ago. His numbers weren't terribly accurate, but that's not the important part. His methods were sound, and they were used later by great thinkers like Hipparchus and Ptolemy to get more accurate sizes and distances. They actually did pretty well, and all over 1,000 years before the invention of the telescope. And I think it also says a lot that these ancient thinkers were willing to accept a solar system that was at least millions of kilometers in size. But at this point, things got sticky. Planets are pretty far away and look like dots. Our methods for finding distances failed for them, for a while at least. In the 17th century, Johannes Kepler and Isaac Newton laid the mathematical groundwork of planetary orbits, and that in turn made it possible, in theory, to get the distances to the planets. But there was a catch. When you do the math, you find that measuring the distances to the other planets means you need to know the distance from the Earth to the Sun accurately. For example, it was known that Jupiter was about 5 times farther from the Sun than the Earth was, but that doesn't tell you what it is in kilometers. So how far away is the Sun? Well, they had a rough idea using the number found by the Greeks, but to be able to truly understand the solar system, they needed a much more accurate value for it. To give you an idea of how important the distance from the Earth to the Sun is, they gave it a pretty highfalutin name, the Astronomical Unit, or AU. Mind you, not an astronomical unit, the one. That's how fundamental it is to understanding everything. A lot of methods were attempted. Sometimes Mercury and Venus transit or cross the face of the sun. Timing these events accurately could then be used to plug numbers into the orbital equations and get the length of an AU. Grand expeditions were sent across the globe multiple times to measure the transits and didn't do too badly. But our atmosphere blurs the images of the planets, putting pretty big error bars on the timing measurements. The best they could do was to say the AU was 148,510,000 kilometers. Plus or minus 800,000 kilometers. That's good, but not quite good enough to make astronomers happy. Finally, in the 1960s, astronomers used radio telescopes to bounce radar pulses off of Venus. Since we know the speed of light extremely accurately, the amount of time it takes for the light to get to Venus and back could be measured with amazing precision. Finally, after all these centuries, the astronomical unit was nailed down. It's now defined to be 149,597,870.7 kilometers. So there. The Earth orbits the Sun on an ellipse, so think of that as the average distance of the Earth from the Sun. Knowing this number unlocked the solar system. It's the fundamental meter stick of astronomy and the scale we use to measure everything. Having this number meant we could predict the motions of the planets, moons, comets, and asteroids. Plus, it meant we could launch our probes into space and explore these strange new worlds for ourselves, see them up close, and truly understand the nature of the solar system. And it's even better than that. Knowing the astronomical unit meant unlocking the stars. We have two eyes, and this gives us binocular vision. When you look at a nearby object, your left eye sees it at a slightly different angle than your right eye. Your brain puts these two images together, compares them, does the geometry, and gives you a sense of distance to that object. And you thought your teacher lied when she said math was useful in everyday life. We call this ability depth perception. You can see it for yourself by doing the thumb thing. As you blink one eye and then the other, your thumb appears to shift position relative to more distant objects. That shift is called parallax. The amount of shift depends on how far apart your eyes are and how far away the object is. If you know the distance between your eyes, we'll call this the baseline. Then you can apply some trigonometry and figure out how far away the object is. If the object is nearby, it shifts a lot. If it's farther away, it shifts less. It works pretty well, but it does put a limit on how far away we can reasonably sense distance with just our eyes. Stars are a bit beyond that limit. If we want to measure their distance using parallax, we need a lot bigger baseline than the few centimeters between our eyes. Once astronomers figured out that the Earth went around the sun rather than vice versa, they realized that the Earth's orbit made a huge baseline. If we observe a star when the Earth is at one spot, then wait 6 months for the Earth to go around the sun to the opposite side of its orbit and observe the star again, then in principle we can determine the distance to the star assuming we know the size of the Earth's orbit. That's why knowing the length of the astronomical unit is so important. The diameter of Earth's orbit is about 300 million kilometers, which makes for a tremendous baseline. Hooray! Except, oops, when stars were observed, no parallax was seen. Was heliocentrism wrong? No. It's just that stars are really and truly far away, much farther than even the size of Earth's orbit. The first star to have its parallax successfully measured was in 1838. The star was 61 Cygni, a bit of a dim bulb, but it was bright enough and close enough for astronomers to measure its shift in apparent position as the Earth orbited the sun. 61 Cygni is about 720,000 astronomical units away. That's a soul-crushing distance, well over 100 trillion kilometers. In fact, that's so far that even the Earth's orbit is too small to be a convenient unit. Astronomers came up with another one, the light year. That's the distance light travels in a year. Light's pretty fast and covers about 10 trillion kilometers in a year. It's a huge distance, but it makes the numbers easier on our poor 8 brains. That makes 61 Cygni a much more palatable 11.4 light years away. Astronomers also use another unit called a parsec. It's based on the angle a star shifts over the course of a year. A star 1 parsec away will have a parallax shift of 1 arcsecond, 1/3600th of a degree. That distance turns out to be about 3.26 light years. As a unit of distance, it's convenient for astronomers, but it's a terrible one if you're doing the Kessel Run. Sorry, Han. The nearest star to the sun we know of, Proxima Centauri, is about 4.2 light years away. The farthest stars you can see with the naked eye are over 1,000 light years distant, but the vast majority are within 100 light years. Space-based satellites are used now to accurately find the distance to hundreds of thousands of stars. Still, this method only works for relatively nearby stars, ones that are less than about 1,000 light years away. But once we know those distances, we can use that information on more distant stars. How? Well, like gravity, the strength of light falls off with the square of the distance. If you have 2 stars that are the same intrinsic brightness, giving off the same amount of energy, and one is twice as far as the other, it will be 1/4 as bright. Make it 10 times farther away, it'll be 1/100th as bright. So if you know how far away the nearer one is by measuring its parallax, you just have to compare its brightness to one farther away to get its distance. You have to make sure they're the same kind of star. Some are more luminous than others. But thanks to spectroscopy, we can do just that. A star's distance is the key to nearly everything about it. Once we know how far it is and we can measure its apparent brightness, we can figure out how luminous it is, how much light it's actually giving off. And its spectrum tells us its temperature. With those in hand, we can determine its mass and even its diameter. Once we figured out how far away stars are, we started to grasp their true physical nature. This led to even more methods of finding distances. The light given off by dying stars, exploding stars, stars that literally pulse, get brighter and dimmer over time. All of these and more can be used to figure out how many trillions of kilometers of space lie between us and them. And we see stars in other galaxies, which means we can use them to determine the actual size and scale of the universe itself. And all of this started when some ancient Greeks were curious about how big the Earth was. Curiosity can take us a great, great distance. Today you learned
So what we've seen in this video is the basis of where we're going to start this module. Looking at a few of the comments, so I want to talk about setting up a telescope in Africa. So we have 2 telescopes currently in South Africa. It's the Hartebeest Hoek telescope, actually free, Cat7, and we have Meerkat. There's a telescope currently being refurbished in Ghana. We have the HESS telescope in Namibia. So there are telescopes in Africa. But the problem is, if we want to observe a black hole, we need to go up to 230 gigahertz. So that means we're looking at X-rays. That means we need equipment or telescopes that is specifically built to look at X-rays, where the Hartebeest Hoek telescope cannot look at X-rays due to imperfections in the surface and also the location of the telescope. So we have too much water vapor in the atmosphere. And the same with Meerkat, it's at a better place, but again, the telescope surface area has a bit of imperfections. It's not designed for X-rays. So if you look at X-rays, your wavelengths is more or less a millimeter in size and smaller. So therefore, South Africa needs to build a millimeter telescope. And then astronomy is interesting. What implications does it have with our reality or technology? So the technology being developed for astronomy will later on appear in our everyday lives. So think about cell phones. The idea of cell phones started with the Apollo missions to land on the moon. They need to get radio signals up there and devices to speak to the astronauts. And that single-handedly led to cell phones. If you take, for example, our Google Maps, Apple Maps, Waze and everything to navigate, that came from space and astronomy research. So for this lecture, we are going to talk about what is the nature of astronomy? What is the nature of science? The laws of nature, numbers in astronomy. Where are we in the universe? The sky and time scale of the universe, history of astronomy, and important astronomy discoveries. Before I continue, does anyone have questions so far? Is everybody still awake? Okay, awesome. So one thing about my classes is I'm going to try and keep my classes as interactive as possible. So feel free to stop me anytime and ask questions. Feel free to interrupt me. Use the chat function in Blackboard Collaborate, unmute your mic and talk to me in a class if you are up for it. The possibilities are endless of what you guys want to do and how you guys want to communicate. So what is the nature of astronomy? So astronomy is defined as the study of the objects that lie beyond our planet Earth and a process by which these objects interact with one another. We will see, though, that it is much more. It is also humanity's attempt to organize what we learn into a clear history of the universe, from the instant of its birth in a Big Bang to the present moment. Just something interesting, if you write on the lecture slides, not just your own screen, it is everybody else's screen that can see it as well. In considering the history of the universe, we will see again and again that a cosmos evolves. It changes in a profound ways over long periods of time. For example, the universe made the carbon, the calcium, and the oxygen necessary to construct something as interesting and complicated as you. Today, many billions of years later, the universe has evolved into a more hospitable place for life. So what is the nature of astronomy? Do you guys recognize this image? So this is a conceptualized image of the Big Bang and how the universe came into being and how the universe is still expanding today. So we had a Big Bang, and from the Big Bang, we had our cosmic dark ages. The first stars started to appear roughly 100 and 180 million years ago. Black holes and accretion disks happened 250 million years ago. Then you have the realization period. Modern galaxy starts to form, and now it's 13.8 billion years later, and this is where we are now. So if we look at our time scale, if you put it on a nice axis, we have our Big Bang. Then here we have a number of years. So 400,000 years after the Big Bang, we started entering the dark ages. So everything was still in, we call it the cosmic soup. 560 million years after the Big Bang, the first light starts to appear due to the first stars being formed. And here we are today, 13.8 billion years later, with stars, galaxies, planets, and all of these interesting phenomena we can observe. So is the energy from the Big Bang still being experienced today? For example, like water drops and ripples. Is the Big Bang still sending out ripples to this date? Yes, that is something we are going to discuss in one of our lectures as well. But if you turn on an old analog, yes, Mr. Serfontein, you are correct. So if you turn on your old analog TV and you see that snowflake sound, the same with radio stations. If you are tuning analog radio and you're in between two different stations, you hear that noise. That is the remnants of the Big Bang we are still hearing and seeing. And that is sitting at more or less 22 megahertz. So do we know what caused the Big Bang? We have no idea what caused the Big Bang. And that is what cosmologists is trying to figure out. So what is the nature of science? So which chapters in the textbook is the work we are conveying today part of? So this is chapter 1 of the textbook. What's your opinion on astrology? Astrology is rubbish. How can a star sign determine what you will do in the future and how it will influence your life? So one thing you will quickly realize about me, I'm all for science, and everything I do is based on facts and science. And like Neil deGrasse Tyson said, science is true whether you believe in it or not. And the other thing you will also realize in my classes, I will joke a lot about, is I will do a lot of Windows bashing. So for your scientific careers, I will do a lecture on that as well. I'm advising you guys to start learning Linux systems, but that's a discussion for a completely other day. So what is the nature of science? The ultimate judge in science is always what nature itself reveals based on observations, experiments, models, and testing. Science is not merely a body of knowledge, but a method by which we attempt to understand nature and how it behaves. The method begins with many observations over a period of time. From the trends found through observations, scientists can model the particular phenomena we want to understand. Such models are always approximations of nature subject for further testing. So does the Big Bang correlate with Darwin evolution? Yes, it does. So one thing we will learn in this module as well, the universe is also still evolving. So from this slide, let's start a little bit of a discussion. So what do you guys imagine is the scientific method? And how does that fit into the nature of science? That is a really good question, but later on in this module, we will learn about a few constants in the universe that shows that the universe is expanding. So let's look at your comments. So hypothesis, experimentation, observation, and repeat. Yes, that forms the basis of the scientific method. So systematic method of developing and testing ideas, that is correct. It's the basis of experimentation, that is correct. We observe the nature and bring forth hypothesis, that is also correct. That's a very nice definition. Trying, failing, working out what went wrong and trying again, that's exactly what happens in a scientific career. So those steps they taught in bio, yes, that's those steps. So will it evolve into a point where it will be over-evolved and like this integrate? That's something we don't know. So that is something cosmologists are still working on. So will the universe ever stop expanding? Currently, all models suggest no. Do we have to do any pre-lessons prep work we can have just switch up to live classes? So you don't have, so I know you guys are extremely busy, you have a lot of modules, so you don't have to prepare for my lessons and you can just sit into my lessons. But if you have time and you want to do a little bit of prep work, I will upload the slides before the lecture, then you can go through it and prepare, and I will usually tell you which chapters we're doing what week. Then you can just go through it if you want to. It's a pleasure. So, one of the ideas of nature of science is, we can see here from a couple of 100 years ago, the belief was Earth, so right now we have Earth is in the middle, we have the stars moving around us, the moon, the sun, and sun is moving around Earth, and it's believed that the Earth was the center of everything. And back then, due to the observations they could make, it was believed that this is true. But then we got a better understanding of what is going on. So then we started realizing, well, the sun is in the center and we are moving around the sun. And here we have different objects orbiting the planets as well. So we had to adjust our model, and that is the nature of science. So when they first propose new models or ideas are sometimes called hypotheses. You may think there can be no new hypothesis in science, such as astronomy, that everything important has already been learned. Nothing could be further from the truth. Resolving these issues will require difficult observations done at the forefront of our technology, and all such hypotheses need further testing before we incorporate them fully into our standard astronomical models. This last point is crucial. A hypothesis must be a proposed explanation that can be tested. The most straightforward approach to such testing in science is to perform an experiment. If the experiment is conducted properly, its results either will agree with the predictions of the hypothesis, or they will contradict it. If the experimental results is truly inconsistent with the hypothesis, the scientist must discard the hypothesis and try to develop an alternative. If the experimental result agrees with predictions, this does not necessarily prove that hypothesis is absolutely correct, but perhaps later experiments will contradict crucial parts of the hypothesis. But the more experiments that agree with the hypothesis, the more likely we are to accept the hypothesis. So my slides have been cut off. So I set this up last year, so I think I need to just reformat it a bit. But hypothesis as a useful description of nature. So are you all familiar with the black sheep analogy with the scientific model? So if you go out to farms, into the countryside, and you see different sheep, what is the first image you think of a sheep? What color is a sheep? Yes, so we set up a hypothesis, and hypothesis set up all sheep are white. But does that actually mean all sheep are white? Exactly. So to contradict that hypothesis, all we need to do is look at one black sheep. So that contradicts our hypothesis. And then we need to restructure our hypothesis, saying sheep can be black and white, and they are grazing in such fields. So this is where the scientific method comes in, and how we redefine the hypothesis of what we are trying to observe and what are we trying to figure out. So how would you guys classify astronomy? What type of science is astronomy? Yes, it forms part of physics, but what I'm looking at is astronomy is an observational science. So to figure out what's happening in the universe and what's happening in space, we need to observe it. And from the observations, we can start to understand physics and to create mathematical models of what is going on. So much of astronomy is also a historical science, because astronomy is a couple of thousand years old, and everything we learn from astronomy is built on by the work of previous. It's like the quote that Neil deGrasse Tyson has used, and Albert Einstein has used it, and Stephen Hawking as well. I've seen further than anyone by standing on the shoulder of giants, meaning you use the giants of the past work to continue your work, and that in whole will contribute to the science. So here we can see we are in the center. Then here we can see the Council of Giants, so that means giant stars, large galaxies. And all bright galaxies nearer than 20 million light years can be seen in this image. So let me go back a slide. I want to have a discussion first on this without you guys seeing it. So what would you guys say is the laws of nature? What are the laws of nature? How can we describe the laws of nature or define the laws of nature? yes, you can say it's physics, but what is the laws of nature? So let's have a little bit of discussion on it. So see a comment, limits to what we're capable of. Yes. Survival of the fittest. Yes. Cause and effect. That's more in the correct direction. So physical quantities which govern how matter behaves. Yes. Now we are looking at answers we're looking for. Yes, so gravity is a law of nature. So over centuries, scientists have extracted various scientific laws from countless of observations, hypotheses, and experiments. These scientific laws are, in a sense, the rules of the game that nature plays. One remarkable discovery about nature is that the same laws apply everywhere in the universe. The rules that determine the motion of stars so far away that your eye cannot see them are the same laws that determine the arc of a baseball after a batter has hit it out of the park. Know that without the existence of such universal laws, we could not make much headway in astronomy. This is not to say that our current scientific models and laws cannot change. New experiments and observations can lead to new, more sophisticated models. Models that can include new phenomena and laws about their behavior. The general theory of relativity, proposed by Albert Einstein, is a perfect example of such a transformation that took place about a century ago. It led us to predict and eventually to observe a strange new class of object that appears as that astronomers call black holes. Only the patient process of observing nature ever more carefully and precisely can demonstrate the vitality of such new scientific models. Thus, the classical laws of physics not apply to quantum physics. So that is something interesting. So at quantum physics, our understanding does a different else. So there's a few places in quantum physics where normal classical mechanics contradict to one another, but that's a discussion we're going to have in this module as well. So is the black hole in Interstellar an accurate representation? So not really. So, but we also cannot say that's why it's a sci-fi movie. Till they are at the event horizon, that is accurate. But after the event horizon, we have no idea what's going on. So a black hole is a region of space that is so dense that no matter or radiation can escape it. So who is the person in the image on the left? Yes, that's Einstein in his 20s. So in 1915, Albert Einstein developed the theory of general relativity, where the theory shows that gravity influences the motion of light. And here we can see Albert Einstein's equation for general relativity. So this is called the field equation for general relativity. So this is not the equation you're going to use for this course. You don't need to memorize it. This is just something interesting I thought to show you guys. So what do you guys think before we continue? What is the limitation we have in astronomy or in science? What is the biggest limitation in science? So that is right. So you are thinking a bit too complex. So the biggest problem in science is actually a simple problem. So the limitation we have, the laws of nature, is a language limitation. So how do we communicate what we are observing? How do we understand what the universe is saying to us? So something quite interesting, that we're going to discuss this in a later chapter as well. But have you guys realized that about 75% of all stars has Arabic names? And if you think about algebra, where do you think the word algebra comes from? Yes, Arabic. So if you think about Arabic, so if you go back to the year 1200, 1300, 1400, the science center of the world was in the Middle East, so Arabic. So that's why the math we are using has a lot of Arabic numerals, Arabic symbols. But during the Middle Ages, something in the Middle East completely changed and they disregarded math. And there hasn't been any much contribution to the scientific community from the Middle East ever since. But going back to the 1200s, 1300s, 1400s, that was the epicenter of science. So our language that we use to describe the universe, understand the universe, is math. And the universe speaks to us in math. So for the rest of your academic careers, even if you stay in academia, do research, if you go to industry, there's one thing I want you to take home. So if from tonight's lecture, there's only one thing you remember and take home, this is it. And that is that math is not math, but math is a language. And that's the language the universe speaks to us. So, how do you practice a new language or learn a new language? That is by practicing. So, you guys need to learn a new language of how the universe communicates to us. And to understand the universe in that language is math. So what's your take on white holes? Another name for a white hole is a wormhole. So in sci-fi movies, we can go into a wormhole and it spits us out somewhere else that can be very far away. So theoretically, and Einstein has written a few papers on that as well, white holes, or a better word I like to use, wormholes, is possible, but we haven't seen any evidence of it and we haven't observed any yet. So to understand our basic math for astronomy, we need to look at numbers in astronomy. So in astronomy, we deal with distances on a scale you have never have thought about before, with numbers larger than any you may have encountered. We adopt two approaches that make dealing with astronomical numbers a little bit easier. So what does a black hole do to matter? So far, we don't know. Our understanding of physics breaks down inside a black hole. So right now we have the scientific notation of numbers. So we can go from 10 to the power minus 6 to 10 to the power 9. And that is the range of numbers we will work with. So secondly, we need to define a light year and other convenient units. So in a video that we see is the astronomical units, so the average distance from the Earth to the Sun. And for all calculation purposes, that is 150 million kilometers, or 1.5 times 8 to the power 10 to the power 8 kilometers, or 150 million kilometers. And that is something important we are going to use. So if you think about what's the distance from Earth to Saturn, that's about 9 astronomical units. So numbers in astronomy. So light years, distance light travels in 1 year. So it's 3 times 10 to the power 5 kilometers per second. So 300,000 kilometers per second. So light will go 7.5 times around Earth in just 1 second. So 1 light year is 36,000 AU, and that equals 9.5 times 10 to the power 12 kilometers. And the closest star to us, Proxima Centauri, is 4.2 light years away. So if we look at this a little bit more closely, light from the moon to the Earth will reach us in 1.3 seconds. Light from the sun to Earth will reach us in 8 light minutes. Light from Sun to Neptune will take 4 hours. The light from Proxima Centauri to our own sun will take 4.2 light years. Light for our sun to reach the constellation Polaris will take 433 light years. The light of our sun to reach the center of our galaxy, the Milky Way, will take 100,000 light years. And our closest neighboring galaxy is the Andromeda Galaxy, and light from our Milky Way galaxy to reach the Andromeda Galaxy will take 2.5 million years. So what do I think about Planet 9? So Planet 9 is a rumor that goes on, or Planet X. So it says there has to be a 10th planet, or rather 9th planet now, because Pluto is not a planet, out there, but with any observations, we cannot see it. And if we do calculations, we can calculate. So there should be a gravitational pull left behind it, and we can't see gravitational pull, so it's just a hoax. So, but isn't the Earth's orbit elliptic? So does the distance to the sun change at points in its orbit? Yes, the orbit is elliptic. So let me get a whiteboard out. So just to give you the distance from the AU. So if we draw this, and we have the sun over here, then the orbit around the sun will be elliptical. So the distance right here is defined as 1 astronomical unit. And this distance here is also defined as 1 astronomical unit. The distance over here, this will be roughly 800 million kilometers shorter. And this will be also roughly 800 million kilometers shorter than 150 million kilometers. So on average, we are 150 million kilometers away, and that's why we are taking the average of 150 million kilometers, and that is the AU. Let me just get back to the slides. So what if light doesn't travel at the same speed, but instead travels at infinity, speed going in the direction? So that is something we can confirm. We have very accurate measurements in pressure chambers and vacuums that we know what the speed of light is, and nothing can travel faster than the speed of light that we know of so far. And I say, does every black hole contain a singularity? So that is something we're going to discuss later in this module as well. But The black hole is a singularity. Another word for a black hole is a singularity. So now we are going to look at the parsec. So a parsec is the angle subtended by 1 AU is 1 arcsecond. So the distance is defined as 1 parsec. Astronomer can measure angles very carefully. A full circle is 360 degrees. Divide by 1 divides into 60 parts, and that gives arc minutes. Divide by 1 degree gives into 60 parts, give arc seconds. So 1 parsec is 3.26 light years. So to explain this, if we are, let me get the pointer out. Can everybody see the pointer? So if this is the sun and here is Earth orbiting the sun, so this means this distance here is 1 AU, this distance here is 1 AU. So if we are in a spaceship and we go far, far, far away from our own solar system and we look back onto our own sun and onto Earth, and we see Earth here and Earth again here, the angle that this makes is, we have this as 1 arcsecond, this angle. So this means this is 1 parsec. So this is, just to remember, so D is parsecs and the P is an arcsecond. So with this, we can convert between the two and do a little bit of rudimentary calculations. Is everyone following? Mr. Pretorius, where are you lost? Or the CEO, another no. So where are you guys lost? How can I repeat it or explain better? What part don't you understand? Okay, so let's explain this from the beginning. So let's go back into our spaceship. We are far away from Earth, and we look back to the sun and Earth. So now we are 1 parsec away. But to keep us in mind, Earth is a circle that can be divided into 360 degrees. So if you take 360 degrees and we divide it by 1 degree, we can get 60 equal parts. So remember, we have degrees and we divide it by 60, so we get 60 equal parts. Divided by 1 degree again, and you can get another 60 parts. So that is arcseconds. So then we just have basic algebra. So from here, we have, let me see if I can write on this just to make it a little bit more clear. So we can divide this into a triangle. And from the triangle, we know this angle is 1 arcsecond. So this is one, I'm just going to write arc for arc S for arcsecond. We know what this distance is. This distance is 1 parsec. And we know what, let's get another color. This distance is, that is 1 AU. So the parsec is defined. If we have this angle right here, and we have this length right here, then we need to determine this length. And that is the formula right here. So this one right here is actually 1 AU, where P is arc seconds and D is parsecs. So if we do the calculation and we want to find out what is a parsec, so D is 1 astronomical unit, divide by parsec, 1 arc second, and that gives us the parsec. But for all intents and purposes for this course, all that you need to know is 1 parsec equals 3.26 light years. So where are we in the universe? Yes, that is basically trig. So if we were on campus in a lecture hall right now, I would show you this now, an image of campus, and our class would have been right in this building right here. So if we zoom out further, what will we see? So if we zoom out, we can see the Greater Pretoria, and here we can see Hartbeespoort Dam. So if we zoom out more, we can see South Africa and our neighboring countries. If we zoom out even more, we can see the curvature of the Earth. If we zoom out more, we can see the Earth in a whole. Now we're not zooming out in a constant ratio. So if we zoom out even more, we can start seeing the moon. That is at 380,000 kilometers. If we zoom out more, we can start seeing the sun and our entire solar system. If we zoom out more, here we can see the sun. We can see the asteroid belt between Jupiter and Mars. Here we can see the Oort cloud and the edge of our local solar system. Here we can see the closest star to us, Alpha Centauri. So if we zoom out further, what do you think we will see? Yes. So if we zoom out further, then we start seeing the Milky Way galaxy. And here we can see the large Magellanic Clouds. That is two large and small Magellanic Clouds. That is two smaller galaxies orbiting our own galaxy. So if we zoom out further, what do you guys think we would see? Yes, you are correct. So if we zoom out further, we will see our local galactic group, and that is where the closest galaxies to us is grouped together. So if we zoom out further, what do you guys think we will see? Almost there. So if we zoom out further, all of these dots and lights are galaxies. So if we zoom out further, then we can see the universe itself and where we are today. So to put everything in perspective, if we put the Big Bang on an almanac, then, okay, I'll continue on saying Andromeda Galaxy will collide. Yes, eventually in about 70 billion years, Andromeda Galaxy will collide with our galaxy. That is something we will also discuss later in this module. So if we put up a time scale of the universe to see how everything happened, we can see the Big Bang occurs in January. Our own Milky Way galaxy starts forming in May. Our own solar system starts forming in September. Earth's atmosphere begins oxidation in October. First complex life forms appear in November. And then when we look in December, everything happens in December. So vertebrates appear on the 19th of December. Land plants on the 20th of December. Dinosaurs appears on the 25th. Mammals on the 26th. Dinosaurs became extinct on the 30th, and humans starts to appear on the 31st of December. So putting this together, and we look at some of the history of astronomy. Here is some of the key persons in astronomy, also on timescale. So 2000 BC, the Chinese played a big role. At 1000 BC, Babylonians and Greeks. At 0, we get Ptolemy. Then at 1000 years, we get Tycho Brahe, Copernicus, Johannes Kepler, Isaac Newton, until we are here today, 2000 years later, the Hubble Space Telescope, Chandra X-ray Observatory, and now the new James Webb Telescope. So this is just another view of explanation of what each of these, or one of the most important discoveries in history. So here we can see Albert Einstein discovered a special theory of relativity. So 1999, launch of the X-ray Space Telescope. So before we continue on this slide, what would you guys say is some of the most important discoveries in the history of astronomy? Telescopes, expansion of the universe. Yes, so all of that put together. So the first thing is pattern recognition. Humans have been looking up to the sky and making observations since the earliest ancient civilizations, and likely before that too. The simple power of pattern recognition is considered the separation point between sentient and non-sentient beings. Another important discovery is Earth moves around the sun. So in 1543 AD, when Copernicus became the first person to demonstrate the math behind such an insane idea, he was universally ridiculed. In fact, the heliocentric model was so revolutionary that Copernicus was actually afraid to publicize it. However, once the idea was finally accepted, it eliminated many problems with all the astronomical studies and is considered the first major realization of our place in the universe. We realized that the sun is a star and not a god, and that we aren't located at the center of the universe. And the second thing is Earth's move, or third, Earth's moves around the sun. So in 1543 AD, when Copernicus became the first person to demonstrate the math behind such an insane idea, he was universally ridiculed. In fact, the heliocentric model was so revolutionary that Copernicus was actually afraid to publicize it. However, once the idea was finally accepted, it eliminated many problems with older astronomical studies and is considered the first major realization of our place in the universe. We realize that the sun is a star, not a god, and that we aren't located at the center of the universe. Then, Kepler's laws. Johannes Kepler proved that the planets moved around the sun in elliptical orbits, rather than perfect circles. In 1609, this was revolutionary because it meant that the distance between the planets and the sun changed over time. Finally, the world understood the reason behind the seasons and apparent motion of planets. Without these discoveries, astronomers would have had a much more difficult time trying to explain why the sun's influence on Earth changes and why the speeds of other planets seem to vary over time. Then, Jupiter's moons. Galileo discovered 4 moons of Jupiter in 1610 using a telescope that he designed and created himself. They were the first moons discovered that didn't orbit Earth, making them the most important piece of evidence for Copernicus' model of heliocentrism. This was tangible proof that planets other than Earth had moons and that we weren't unique as what we thought. Then Herschel's map. Astronomer William Herschel and his sister Caroline systematically mapped the night sky, listing thousands of stars and nebula in an almost 5-decade process. Published in 1834, this map revealed the shape and size of the Milky Way, which turned out to be disc-shaped rather than a sphere. He also discovered Uranus. Then the theory of relativity. Before Einstein knocked it out of the park with his theory of relativity, the world of astronomy strictly obeyed Newton's 3 laws. Everything changed when Einstein argued that motion was relative and that light could be affected by gravity. The possibility that mass could warp space-time and that large enough masses could even bend light shook the scientific community because light was considered an absolute constant. The theory revolutionized astronomy and solved many problems that had been deemed impossible with Newton's confining laws. Then we have the expanding universe. When Edwin Hubble told the world that the universe is expanding, it was groundbreaking, so to say the least. After tracking the movement of other galaxies, which he was also the first to discover, he concluded that they are moving away from us, while also constantly accelerating. He also concluded that most of the nebula was visible in the night sky were actually galaxies. This provided further evidence to support the theory of the Big Bang and changed our conception of the universe. Then we have the cosmic microwave background radiation, or the leftover image of the Big Bang we can detect. So unfortunately, uniformly defined radiation that fills the universe was discovered quite accidentally by 2 Bell telephone employees in 1964 while working on satellite communications. Since light from an object 1 light year away takes 1 year to reach Earth, the cosmic microwave background radiation functions like a snapshot of the universe. The implications of this discovery were profound, since the uniformity of the radiation appears to confirm the notion that the universe originated as a single event from which everything else flows. This fact supports the theory of an expanding universe and therefore the Big Bang. Then, extrasolar planets. An extrasolar planet, also known as an exoplanet, is a planet found outside our solar system. The existence of exoplanets was not all that surprising, but the method by which they were discovered has changed the course of astronomy. Nearly 3,000 exoplanets have been discovered since 1988. Roughly 1 in 5 Sun-like stars have Earth-sized planets with the habitable distance from the star. Assuming there are 200 billion stars in a galaxy, Milky Way galaxy, that would mean 11 billion habitable Earth-like planets in the Milky Way galaxy alone. And then lastly, the image of a black hole. So I'm going to leave you tonight with a bit of food for thought. So the molecules that comprise our body are traceable to the crucibles of the centers of stars. These atoms and molecules are in us because, in fact, the universe is in us. And we are not only figuratively, but literally stardust. And that, ladies and gentlemen, is our lecture for this evening. So I will upload the study guides in the next day or so. I just need to finalize a few things. Otherwise, have a great week. I will see you all in next week, Monday's class. So I hope that you guys enjoy this lecture. So you are more than welcome to log off now. I will be active for a minute or two if you have any questions. Otherwise, have a great evening and good luck with the rest of the week.